Good morning, class. I hope everyone's doing well. As I told my students yesterday, we're back into our springtime weather. I was getting used to the cooler mornings, but you know that's what we have in Houston. So enjoy the warmer weather if you like that right now, and I'm happy for you if that's the case. What we want to do today is to basically take this week to finish up our work on trigonometry. Today, we want to discuss some more very useful identities that you will find equally helpful when you move into the calculus sequence. All the trig we've done so far has been extremely foundational and has provided us a good, solid understanding of the arithmetic of the unit circle and the triangle. So what we want to do is to look forward a little bit to see how we can combine certain ideas to produce other identities that will be very helpful, not only in calculus, but in physics and engineering. Trigonometry is just one of those topics that is so extremely useful with motion, with geometry. I mean, there are countless uses for trigonometry. So we want to make sure that you have a good, solid foundation in that before you proceed to calculus. So let me go ahead and share my screen. And what I'm going to do is I'm going to add an example. We've had, there's an example in your 6.6 with the law of cosines that actually requires that you know a particular exact value. And I left it in the homework section, hoping that you would maybe think about looking into some of the further identities. If you check the formula sheet on your Blackboard page, or you looked at something in WebAssign and it said exact answer. And here was one of the terms that you needed to know exactly. And let me write it down. So this is kind of giving us a starting point for our lecture today. You had a 75 degree angle, a 30-degree angle, and a 45-degree angle. And so the 30 degree and the 45-degree angle you find on the unit circle. But you have this 75-degree angle, and there's no allusion to any type of approximation with the problem. And it says apply the law of cosine 3 times, and then solve for x, or the length of the side of the polygon. So this is something that we need to figure out, because basically we have all kinds of interesting identities, but we know 75 is just 30 degrees, or 30 plus 45. And if we're working with degrees, which is very important, a lot of you will leave out degrees and wonder why your answer is wrong. Well, if you don't put that symbol there, WebAssign reads it as radian measure. So it's very important to be specific about what you mean. So when we look at this, we're thinking, is there something here that we can actually work with that will allow us to compute this exactly? So that's what we're going to do now. Now, this first theorem actually has 6 parts in it, and I'm just going to write it down. And then we're going to look to see how we can actually prove them. We just really need to do one clean proof, and then the rest just fall out of the woodwork very easily, like most of the problems that we work with in trigonometry. So what we're going to do is we're going to let A and B, I'm going to use uppercase letters so they're real easy to see, be real numbers. And we're going to assume that whichever trig function we're working with, that we have these well defined, that A and B are actually in the domains. So I'm going to write down several identities. These are going to be called the addition and subtraction formulas. And of course, like all the identities, you need to commit these to your knowledge base. What we're going to find with these identities, especially the first 4, is that they give rise to other identities, just like the Pythagorean identities, and we will find actual great use for them. So When I say commit to your knowledge base, you're going to know them because you use them a lot. Memorizing them is fine, but you're going to know them because you actually use these particular identities quite a bit. Now, the first one, this is not going to be what we're going to prove. We're actually going to prove the cosine one, but I'm going to start with the sine. So we're going to have the sine of a sum. Unfortunately, this is not additive. This is not sine of A plus sine of B. It would be nice if it were, but it's not that simple. So we get sine A, cosine B, and the way I write it, I just flip the arguments. Sine B, cosine A. Okay, and then you look at that and say, well, I can commit that to memory, but it, again, it's not that difficult either way. Two, so we'll show why all of these are true, and then we'll use some of them. And we'll see how we can get an answer for this so you can finish your WebAssign problem. And then, of course, if we know one, we can easily get two just by some smoke and mirrors. So this will be sine A, cosine B, now with a minus sine B, cosine A. Now I'm just going to go ahead and put 3 over here. We'll have the cosine of a sum. That's the one we're going to prove. It's real easy to prove just using the unit circle and basically the congruent arcs subtended by congruent chords. That's an argument we've used before and very, very simple. Now, this one will actually allow us to solve this problem here. So this is actually cosine A, cosine B, minus sine A, sine B. Again, sometimes I'll use arguments, ladies and gentlemen, that are easy to see. I'll use U's and V's sometimes, but sometimes students mistake a U for a V, and so I try to write it like a Greek nu, but I'm trying to make these very obvious so you can see them. Or, well, let's look at the difference, and again, that'll just be a small change, A minus B. The minus changes to a plus. So those are the first 3 where basically when we think about this, let me get a little more focus here. When we think about these particular, oh, I just lost my stop share. I'll tell you, trying to clean up, there we go, let's come back. That looks pretty clear. Let me just get a little bit lighter. There we go. Obviously imperceptible, right? So now when we look at these, we're thinking, well, if we can prove this, we can easily get this, and then we can use cofunction identities to get this. And then the other 2 actually involve the tangent function, which again, that's just sine over cosine. Now, the tangent identities don't get as much use, but they're still, you know, something that we want to think about. So I'm going to put 5 here, and this will be the tangent of the sum. And this one actually is probably the easiest to remember. It's tangent A. It starts out like it looks to be additive, but it's not. Tangent A plus tangent B. That part's easy to remember. We wish they were all that easy. But then in the denominator, we get 1 minus the product of tangent A and tangent B. So again, that'll be easy to derive knowing 1 through 4. And then 6, of course, we'll just flip the signs here. Tangent of the difference. This will be tangent A minus tangent B divided by 1 plus the product of tangent A and tangent B. So what we're seeing here is that there's a certain uniformity to these identities. And we think, well, you know, that's really nice. We haven't, you know, with the Pythagorean identities remind us of the Pythagorean theorem. That's basically what they are. Okay. And so those haven't been so bad. You know, but then we start doing, you know, the even and odd, and then the inverse trig functions, and they're not as simple to remember, especially if we take inverse cosine of negative x. What does that mean? It's not even, it's not odd. How do we do it? The thing is, these seem to be fairly user friendly, and even if you didn't prove them, you might be inclined to believe them. So what we want to do, before I get to this, I'm sure you're thinking about this. Let's just go ahead and see if we can provide some type of justification for this. And then we can, the rest will just fall out. And we'll do several of those to convince you that these are good. Again, put these on a note card, as will be all the identities we do today. They will be useful. And of course, there's a formula sheet on Blackboard that has all of these, but I know you all like to write your own. I always like writing my own, but if you want to use that as a reference, you certainly may. So what I want to do is just draw a unit circle, very simple procedure here, and work with the arcs and the chords. This just helps to coordinate our logic. And we provide the mathematics to make it a proof. But we like to have some organization to the logic, and especially when we're doing trig and geometry, pictures are very good to organize. Just like if you're doing calculus problems where you're trying to organize the formula from some geometric considerations. So let's do what we know we can do well, which is draw pictures. So let's draw our unit circle. Again, I always tell you your work doesn't have to look like Rembrandt, but I don't want Picasso right now. Picasso's fine for, I guess, when we do more abstract. We're doing abstract, but we want our pictures to look halfway decent. But that's all relative. So it's kind of a little lopsided, but it'll do. Now what I want to do is mark the A and the B, and for purposes of our argument, it doesn't matter if they're positive or negative, but I'm going to start out with two positive angles, and then I'm going to look at the negative of A. And you could flip all that around. It won't matter. We just need to get an angle that's A plus B. And if they're positive, it's easier to see it visually. So this is a visual setup with a rigorous rendering. So let's start with A, an abstract measure of A, which is also going to be the length here, because we're in the unit circle. So this is S1. So now with S1, this will be A. I'll mark it as A. So this will give us cosine A, sine A. Now what I want to do is mark off an angle B. So we'll make it larger. We could be the same size, but let's make it bigger, just so again we appeal to the visual. So we'll draw another angle, and then we'll end up somewhere over here when we add them up. So here, this will be angle B. And I'll mark that there. And so now we'll have cosine B, sine A. Let's not change the definition of sine and cosine, Professor Ron. And now what I want to do is just basically do a visual. We've got B here, and we're going to add A, and I'll push this a little bit over here. So again, just a visual. So here we'll have A plus B. So we'll have cosine A plus B sine A plus B. Often the proofs in geometry get their start from a diagram that, again, that helps to organize. And there's nothing wrong with that. Again, the diagram is not the proof, but it does help us to organize our thoughts. So always use this technique when it can be of service to you. Now what I want to do, so I can do this equal arcs subtending equal chords, I want to write the negative angle here. So I'm just going to come down here and put in negative A. So this is a counterclockwise rendering. So here is negative A. But now, of course, when we define the cosine and sine, the cosine being even just gives us cosine A, but the sine is odd, so the negative will factor. So here we get cosine A, but the additive inverse of sine A, since sine is odd. So here the negative factors, here the negative absorbs. Just remember that cosine even, sine is odd. Now what we can do is notice that here we have the arc distance A plus B, and here we have the arc distance A plus B. And also, let's just go ahead and note that this point is 1, 0. That's the easiest point on the circle. So now what we can do is connect the arcs that are equal, or with the chords that subtend them. This one, and then of course this one. So on the unit circle, these two chords subtend congruent arcs. So they are therefore congruent. So this arc, or this chord, is congruent to this chord. Now what we want to do is just use basic Euclidean distance, but we'll square the distances. So what we want to do, again, like we did the law of cosines, there's no need to throw in square roots. They just get in the way. So equate squared distances. Now, again, you could mark off all of these with labels, but we've done this enough times, we don't have to do that. So just go ahead and put one finger here and one here and do the difference in the X coordinates and the difference in the Y coordinates. We square each of them and add. So we have, well, this will be easy. So we have cosine A plus B minus 1. Quantity squared, just doing Euclidean distance, plus, now just bump over to here and to here, then we'll have plus, now we've got sine A plus B minus 0, so that's just sine of A plus B squared. And now shift to here, the other congruent chord, and take the difference. So this will be equal to, so now we've got cosine B minus cosine A, quantity squared, shift here, plus, let me not cover up the sign, sine B minus the negative, so that's plus sine A, quantity squared. So this should remind you of what we did with the law of cosines, very similar. But again, we were dealing only with the triangles there. Here we have embedded triangles. So you could also affect this proof with just triangles. But since this is just such a nice way to do it with the unit circle, we appeal to that. It's a very elegant way to do this. And now all we have to do is expand this, and our theorem just comes right out. So let's go ahead and square this. So equivalently, we get cosine squared A plus B. Now we take the product and hit it with a 2. So that's minus 2 times cosine A plus B. plus a 1. Square the 1, we have plus 1. Now here we just square it. There was only one term to square. Sine squared a plus b. So we use our lazy notation. The quantity here squared, we just write as sine squared, okay, using our useful notation. Now let's expand this. Cosine squared, we're going to get a lot of Pythagorean identity. Cosine squared b, then the product times 2, -2. I'll just write the cosine a first, alphabetical order. I don't think it matters, but that's fine. And then we square the cosine a. Now do the same here. So plus sine squared plus now 2 sine a sine b plus sine a squared, or just sine squared. Now, well, the hard part was this, and that really wasn't very hard, was it? So notice here when we look at all of this, this is the cosine squared plus the sine squared. That's 1, and we already have a 1, so we get 2 minus 2 cosine a plus b. So again, these add, this is just Pythagorean, that equals 1. So again, we're using just the basics of the unit circle, and now we have a cosine squared, so this equals cosine squared b, and we have a sine squared b, that gives us a 1. And then we have a cosine squared a, and the sine squared a, that also gives us a 1. So we have a 1 plus a 1, that's a 2. And then we have the minus 2 cosine a cosine b, we're just court reporters today, plus 2 sine a sine b. Now, just like we always do, I've done all this symbolically. That's how I have taught you. And then on the 4th test, I expect to see some good write-ups. That's going to be 40 points out of 100. So if you have not been writing your mathematics, you need to get busy because I will require it. And it will be the same for the final exam. Now, the 2's absorb. They're gone. And then all of these 2's that are hanging out, we can just absorb them too. So this will give us a negative cosine a plus b equals negative 2 cosine a cosine b. Oh, sorry. Got rid of the 2, Professor Ron. So get rid of it. I just don't want to let the 2 go. And then plus sine a sine b. But now, of course, we need just cosine a plus b, which we have up here. So just multiply through by -1. So equivalently, cosine a plus b equals cosine a cosine b minus sine a sine b. Now, what's nice about this proof here is that it's not very difficult. Like, it reminds us of the law of cosines. We have to set up some geometry to organize our thoughts, but then the procedure is very algebraic. Again, there are always several ways to go about proving things. What I like to do is to use a proof that actually maybe makes us think a little bit more, but also is reasonable. I mean, if we have to go outside of the box quite a bit, then that just may be the nature of the subject. But here we can stick to the unit circle, our friend, where the trigonometry for us in this particular class started. So now here's number 3. This is 3. So check. Now what we can do, we can make easy access to 4, 1 and 2, and then 5 and 6 will be likewise easy. So let's go ahead and get those, and then we'll finish it off. Now, before, and I don't want to lose the train of thought here, so I want to keep on with these proofs, because if I move away from them, then you'll lose your advantage. So what I'm going to do is I'm going to put this right here where you can see it. There's the formula that we just proved, okay? So now I want to get 4. So what is 4? Well, notice we have cosine A minus B. Well, let's write this so it looks like that with a plus sign. Let's do a little smoke and mirrors. I say that just for humor, but you know what I mean. Algebra is the key. So we now write the difference as a sum. That is now cosine of A minus B is cosine of A plus the additive inverse of B. So now it looks like this. So now we replace A with A, but we replace B with its additive inverse in this formula, since now we have the pattern that we need for this. So this will be cosine A, cosine additive inverse of B, minus sine A, sine additive inverse of B. Now, I've been really big on the even and odd with the inverse trig and all the trig functions, because these concepts are critical. Lack of understanding of even and odd when it comes to trigonometry is destructive. So that's why we spend a lot of time with this. We cannot avoid even and odd when it comes to trigonometry. So now notice, just like we used before in the proof, the cosine of negative b, the negative absorbs because cosine is even. So let me just write it right below it. So this is cosine A, cosine B, just like we had before. We didn't even bother to write it down. Now here, again, the sine function is odd, so the negative factors, but then that negative will absorb this negative. So negative negative will give us plus. So we have sine A, sine B, and we're done with that one. That's number 4. So that was easy, easy. We had to work to get this one, but now we know the relationships between cosines and negative angles and sines and negative angles. And we also know relationships between sines and cosines with the cofunction. So now let's just go to 1 and figure it out. So we have, okay, let me, this is what we're going to deal with now, but we don't have a formula that we're hanging on except the cosine, so we'll go back to that. So now, sine of A plus B, we're going to use cofunction identity. I mean, what else can we use? We want to keep it nice and simple. So now we can say, okay, well, the sine of A plus B will just be the cofunction of pi over 2 minus A plus B. So we have cosine, cofunction, pi over 2 minus A plus B. That's the cofunction identity, okay? Because sine and cosine are cofunctions. So the beauty of the cofunctions is that they work for any triangle, even if it's you know, well, any triangle, so to speak. Regardless of the quadrant, we can always move back to the acute triangle in the first quadrant using the reference angle. So this is applicable to any A and B. That's the beauty of trigonometry. But since we always head back to the first quadrant, we must remember the arithmetic. Where do we terminate? So we know which is sign to apply. That is X positive or negative? Is Y positive or negative, etc. So now we'll just do a little bit of smoke and mirrors again. We'll say cosine of pi over 2 minus A minus B. So now we have this formula right here. We've got this formula. So let's use it, the one we just proved. So the idea here is that by using the cofunction, we have now transformed this to this one, where the B is B, but the new A is pi over 2 minus A. So this is what we call the new A, so to speak. That's the smoke and mirrors. This is the new A. So now let's substitute. So this will be, let's just apply the formula right here, cosine pi over 2 minus A times cosine of B, then plus, now we've got sine of A, sine of the new A, so we have sine of pi over 2 minus A, and then sine B. But now this is just the simple cofunction identity. The cosine of pi over 2 minus A is just sine of A. And now we'll do this and we'll reverse these. The sine of pi over 2 minus A is just cosine of A, but we'll do the sine B first since I wrote that one. So let's write this one first and then cosine A, and we're done. So the cofunction identities are easy. So what we do is when we apply it here, we have what we don't expect. That is, we have a new item here, which we rewrite to get two arguments so we can reuse the cofunction identity. So we use the cofunction identity twice. So again, this takes care of one. And now that, well, I'm not going to say this was easy. That was easy. This took a little bit more work with the cofunction, and you're less understanding of the cofunction because it's a new identity that we use. So this takes a little bit more work, but still straightforward, still easier than this. Now the last one, number 2, we just rewrite use the even odd nature of sine and cosine. So we have sine of A minus B. Let's just again rewrite this as a sum so we can use this. So this will be sine of A plus the additive inverse of B. So we get a new B, so to speak. So again, notice here, so I can help you keep up with these, I just flipped the arguments here. We have sine A cosine B plus sine B cosine A. They're not the same. So to make that connection a little bit easier, I just go ahead and keep the order of the sine and cosine the same and then flip the arguments. That may help you to remember these more easily, but you choose whichever works for you. So now, okay, well, we just use the fact that we have the new B here and apply this. So this will be sine of A cosine of negative B plus now the new B sine of negative B cosine of A. So again, just like we had here, this was the new B, the new B. We have the new B. And now, of course, the cosine is even, so the negative absorbs. So we have sine A cosine B. But now, of course, the sine function is odd, so the negative factors. So we get minus sine B cosine A, and we're done. So not to say that this is just simple. It's not difficult using what we already know about trig functions. So we may have to, mathematics has this type of philosophy, and this type of argument is done over and over. You often have to work very hard to get an initial result, but then other results in the theorem may be similar. And so you use the result you've proven to provide a proof for the remaining pieces of the consequence of the theorem. That is, you have hypotheses, you have the consequences or the conclusions. So this is a standard routine for proving mathematical theorems, and geometry and trigonometry are just wonderful places to begin that journey for you all. As you computer science gurus will be doing plenty of discrete proofs. induction. We're even going to talk about induction in this class. So the pre-cal, along with your high school geometry class, gives you a nice introduction to how we can start the method of proof. Now, for the tangent and the sum and addition, let's just go ahead and knock those out. So this was what, number 5? So remember, tangent of A plus B, we're going to be real simple here because we don't want to work hard. We're just going to write this as sine over cosine. Sine of A plus B divided by cosine of A plus B. Now, of course, we know what these are based on the identities we just proved, and we'll just use a little bit of algebra. So this will be sine A cosine B plus sine B cosine A. And then downstairs, the cosine is easy to remember because you have the same trig function with each product. So you have cosine A, cosine B. These make good for double angle identities, minus sine A, sine B. Now you're thinking, what's wrong with that? There's nothing wrong with that. That's true. That's an identity. I mean, that's true. That is absolutely true. But it's not the form that has become convention. So what was decided upon is that if you multiply and divide by the reciprocal of this term to make this a 1 and to create a bunch of tangent terms, that's the only thing that's done here. And again, this has just become convention. So we'll do 1 over cosine A, cosine B, upstairs and downstairs. Again, this would be a trick that we would use, or an algebraic maneuver that we would use to rewrite this particular expression. This being valid, but not the conclusion that we want from our theorem statement. So when we do that, we just get sine A cosine B. So go ahead and divide cosine A cosine B plus sine B cosine A. Just a lot of writing now, but very simple. Cosine A cosine B. And then downstairs, obviously here, these will absorb, but I'll go ahead and write it. Cosine A cosine B. We'll do this one for number 5, but the other one you can do. We won't. It's the same procedure, so we won't have to repeat this. So divide cosine A cosine B by itself, and then minus sine A sine B cosine A cosine B. So the idea here is that maybe someone thought about this for a while and decided, okay, let's make sure we write the tangent of a sum in terms of tangent functions, you know. But we think these are wonderful here. These are fine the way they are, and they have become the standard. So now notice the cosine B absorbs here, and here the cosine A absorbs. So that leaves us tan, in this case, tan A tan B. So tan A plus tan B. So if you like, just say absorb, just put little boxes around them. Those terms absorb. Now here, of course, we just get a 1. Those are the denominator and numerator are equal. And here we just get a tan A and a tan B. And this has become the standard form for the tangent of a sum. Again, doesn't get as much use as the sine and cosine ones, clearly, but it is an identity that comes up. You're thinking you can make up an identity just on a whim. It may not be something that is used often, but these actually get used. So that's why we learn them. And then of course 6, we'll just go ahead and write down. We'll just do tangent. Well, let's just go ahead and cheat. A minus B. I mean, I'll just go ahead and do it since it's like the other ones. So we get tangent A plus the negative of B. I mean, I did it for this one, so I'll go ahead and the other one. So I'll go ahead and finish it out. So of course, this is the new B, so to speak. So we just use this. So tangent A plus tangent, well, that kind of ran together. Let me do that again. Plus tangent of the additive inverse of B, or negative B. And then we have 1 minus tangent A, tangent additive inverse. I didn't want to imply that you have to do this again. You could, but we just use the technique we've used in the previous two cases. So now, of course, the tangent function is odd. That's a famous odd function, just like the inverse tangent is odd. So the negative factors. So we get tan A minus tan B. This is good practice, ladies and gentlemen. Doing these proofs are actually good practice working with algebra and identities with the trigonometry. So this is something you should know how to do. And then of course here, the negative factors and absorbs the negative here. So this is 1 plus tan A, tan B. So I was honest when I said, once we get the initial equation here, this identity 3, the rest follow from it, so to speak. There's just this cascading effect. So even though this proof requires more time, it's certainly not a difficult proof. It is a very straightforward utilization of geometric consequences of a circle and its chords, namely arcs and chords. So again, we want to, let me go back to here. We want to know these. We need to put these on a note card, and we need to know them. We need to use them and become familiar with them, because that 1 through 4 are actually the basis of many other identities that we'll talk about today. Okay, so now let's look at some more ideas here. Let's just go ahead and go back to the problem that we started out with. So you're doing that law of cosines problem, and you have cosine of 75 degrees. Well, now with the addition formulas, which some of you probably figured out, thinking about this, looking ahead, you can write the 75 as a sum. So if you want to use our new identities to get exact values for certain inputs, then the case would be that you would try or make an effort to rewrite the input as a sum or difference of angles about which you have knowledge. That is, angles from the unit circle that you know their terminal points, and you know exactly what's going on there. So what obviously we'll do what we said initially. We'll have 30 degrees plus 45 degrees. So you can use this in the problem. And that's the main reason I left it in that section. I put it over there during the summer, and I thought this would be a good segue to this argument. So now we'll have cosine 30 degrees, cosine 45 degrees, minus sine 30 degrees, and then sine, let me hold off on the parenthesis here, and then sine 45 degrees. So now you're thinking, oh, okay, well, I know all of these values from the unit circle. So we have square root 3 over 2, cosine 30 degrees, and then cosine of 45 is 1 over root 2. Again, remember, you don't have to rationalize with WebAssign. It's not required. They don't tell you to. As long as it's equivalent to a correct answer, WebAssign is actually your friend, even though a lot of you don't feel that way. You should use a really poor computer algebra system and then find what a nightmare that could be. So you should count your blessings that Professor Ron uses the state-of-the-art WebAssign homework tool and testing tool. It is indeed the best. So now sine of 30 degrees, that's 1/2. And then sine of 45 is 1 over root 2. So now it's like, okay, well, we're done. We have the same denominator, 2 root 2. Of course, you can use root 2 over 2 if you like, and then we have root 3 minus 1. And there is the exact value of cosine of 75 degrees. So you can use that in your computation. The idea here is that when you look at your WebAssign problem, it does not say approximate your answer to 2 decimals or whatever, or the nearest integer or whatever. If you have no instructions for approximating and you approximate, that is clearly a mistake that you know not to make. So you don't have to send me messages anymore saying, oh, Professor Ron, how many decimals do I round? I'm like, you don't round because you weren't told to do it. That's again, just something that I'm trying to train you in so that you will have a better mathematical technique. Now, there's one other lemma that we have in this section, which you're going to use maybe when you get to one of Professor Nate's maybe engineering courses. We will actually use it. I use it in calculus 2. You will also use it in differential equations. It's something that we decide we need when we want to combine a sine and a cosine term with coefficients. So we want to be able to make a combination so that when we graph or we think of a graph of the sum of two functions, we're just looking at one. And here's this lemma. It's very important. So what we want to do is fix A and B as real numbers. They're going to be coefficients. And we'll just let X be a real number, arbitrary. So the idea is that if we have A, some coefficient A times sine of X, and some coefficient B times the cosine of X, it would be nice to be able to write this as one function. And you're thinking, we've got this sine and cosine, sum and addition. Does that help us at all? And it absolutely does. This is actually equivalent to the following expression. It's Pythagorean, see, square root a squared plus b squared times the sine of the sum, x plus phi, where phi, the tangent of phi, is just b over a. So when you think about this particular example and you think about doing it, you're like, oh, well, this reminds me of triangles. So what you can do is think that way when you try to develop some kind of reasoning for it. But this is something, again, you'll see in a differential equations course when you talk about harmonic motion. You'll see this in calculus 2, because it will keep you from having to use the Weierstrass substitution, which is tedious, long-winded, like Professor Ron. So you're thinking, okay, so that's kind of a loaded statement. It tells me about A and B, how they're related to phi. And it basically combines the sum here as one function, which you know how to graph. You would have a shift and you'd have a stretching here or compression. So the idea is that you would know how to graph this using transformations, but here that'd be a little bit more complicated. So this is easier to think about graphically. So what we can do is define, I'll just write that with an uppercase. So declare this. So we could define sine of phi. We can think of opposite over adjacent or opposite over hypotenuse, just like we do before. You can see why Dr. Stewart uses A's and B's. And we can define cosine of phi to be A over the square root of A squared plus B squared. Now, of course, these make sense because these are bounded between 1 and -1. This definition would make no sense if it didn't suit the range of the sine and the cosine. So these would be definitions that would be acceptable. And so now when you look at this, you're thinking, okay, well, we can solve for A and B. So equivalently, A equals square root A squared plus B squared times cosine phi, and B, so this is really an interesting situation. They're defined in terms of themselves. B is equal to the square root of A squared plus B squared times sine phi. And that happens all the time in trigonometry. So these are complicated equations. And so now we can just substitute. Then A sine x I need to append that, sine x plus B cosine x. Let's just substitute. We get square root A squared plus B squared cosine phi sine x plus square root A squared plus B squared sine phi cosine x. But now, of course, we can factor the radical. And then I'll just write the signs first because that mimics the addition formula for sine. So we have sine x cosine phi plus sine phi cosine x. But that's exactly the sum formula for sine, the way I told you you should write it. And so this will just be the square root of A squared plus B squared times sine of x plus phi. So if you want to do these by thinking about a little triangle where WebAssign asks you to write this as one term, this is the formula right here. Very straightforward. So the thing is that now what we're just trying to do is combine some of the trigonometric notions we have into new identities that'll help us with problems. And as you work problems, you may come up with your own type of tricks and identities, like in an engineering class or in a math class to move you to the next level. But of course, if you do that, you have to make sure it's consistent, that you're just not making it up. And that's really what math is all about. Math is not the art of perfection. I mean, if I teach you something and you study it, well, then you know what you're doing and I expect you to execute it correctly. But when you're doing math to learn, the process is like working in a laboratory. You're trying things. I'll try something in a lecture and let's see how this takes us, how this changes the proof or whatever. That part is like doing a lab in science class. Okay, so the experimentation in mathematics is essential. Math is not perfect in that everything you do should be perfect. You should make lots of mistakes when you're learning because the mistakes help you to find the correct path. So the experimentation you do in mathematics is just like what you do in a laboratory, but usually you're doing it with pencil and paper, but it's the same thing. Now, there is an example that I want to think about that has to do with utilizing the inverse trig with our newfound friends. So let's see here. I've got several here. They're all about the same. Let's do an algebraic expression. We've used the sine formula a lot. Let's use the cosine. And I have an example here also with the tangent that I want to use just to get some practice. So let's start with that one. So first, let's go right back to the original inclination for all of this and look at an example. Then we want to write down a bunch of new formulas that we can use when we solve equations. Like we're going to take these formulas and make new ones from them. So first, let's look at the tangent of -5 pi over 12. And we want to compute an exact value. So when you work these problems, have all of your identities handy. There we go. Good old IPEVO. That's the name of the document cam from Japan, IPEVO. Very popular. And so glad that they had some to sell to Professor Ron. So now notice you're thinking, okay, well, we'll do the same thing we did before. First, we'll notice that we have a negative here, which we can already factor because we know the tangent function is odd. So don't deal with negatives when you're working with trig functions. Now, this gives us this, and you're thinking, we're just going to break this up into two pieces because our hope is that these will be easy functions or easy measurements on the unit circle. So we can do 2 and 3 with the 5. So we have 2 pi over 12 plus 3 pi over 12. This is exactly what we did before, but when it was much more difficult when we were doing reference angles and things. So when you look at this, you're thinking, okay, if we reduce these will look just like angles that we know and love from the first quadrant. So we get the negative of tangent, and of course the 2's absorbed to give us pi over 6, and the 3's absorbed to give us pi over 4. So the beauty of these new formulas is that now we can find exact values for inputs that we don't get on the unit circle. So this is what I was saying at the beginning. I'll say we only have certain values on the unit circle because they come up often. And so we use those to actually compute these. Now we don't want to put all of these new values on the unit circle. It'd make it too complicated. So we have these nice identities to find the exact. So let's go ahead and fill it in. So we have the negative. So we've got tangent of pi over 6. This is the sum formula, plus tangent of pi over 4. And then we have 1 minus the product, tangent of pi over 6 times the tangent, you can put a little dot there, just juxtapose pi over 4. So we have the negative, that's we factored. Now, of course, tangent of pi over 6, that's the 1/2 divided by the square root of 3 over 2. So that's 1 over root 3. And of course, tangent of pi over 4, that's our friend, that's just 1. And downstairs, we pretty much get the same thing. We get the 1, and then we get, of course, minus 1 over root 3, tangent of pi over 6 times a 1. So boom, we got the same thing. Now, of course, you could input this into WebAssign and it would smile at you, but let's just clean it up a little bit. We can get a common denominator of square root 3 and then factor it, or just absorb it. So we'll have 1 plus root 3 over root 3, and then root 3 minus 1 over root 3. So now the root 3 is absorbed, and that gives us the negative of 1 plus root 3 divided by root 3 minus 1. Now, if you like, again, this is fine, but let's just get a little practice. I always like to just have some practice with radicals. We can run the negative in and flip it downstairs. So that'll be 1 minus root 3. Again, this would be fine. Now, WebAssign would not have issue with this, would not have issue with this, none of these. They're all fine. They're all equivalent. But if you were thinking back to the very beginning where we said, what if we wanted to rationalize this? This is just extra. This is not something you have to do. You're trying to finish a test, you get in, you get out, okay? But say you're in a physics class and your professor says, oh, we get this, and you think, well, I have this, but it doesn't look like that. Well, then we can rationalize. So we can do 1 plus root 3, 1 plus root 3 with the conjugate method like this. and use your parentheses. Now, of course, this is not required, but you're thinking, well, I want to check to see that I got the same result as my physics professor. So now this is just a binomial. So that's 1 plus 2 root 3 plus 3. And this is just a difference of 2 squares. So this is just going to be 1 minus 3. Again, the square of the square root of 3 is 3. Well, how simple is this? So we've got what, 4 plus 2 root 3. It's certainly not any better, but maybe it looks easier with a minus 2. So now we can just divide by -2 and get a -2 minus root 3. So that would be very simple looking, but on a test, you know, if you, like I say, get in, get out, you know, you can stop here, you could stop there. That might be more to type, a little bit more complicated to type. So it might be easier just to work to here or to here. But the idea is an equivalent answer is all that WebAssign asks. When they want an exact response, any of these would work. So the idea is you don't have to question. Again, WebAssign will give you the green mark, but you have to make sure that what you put in is exactly what you mean. And that's the training that WebAssign is allowing for you. Now, again, we might think, how does this work with the inverse trig? Let's do an example of that and then get to our new found friends with our old friends. So now our new formulas are going to be old formulas, and we'll get some new ones from the old. So let's look at just an exact computation. Now you can use these new identities for algebraic expressions in X, or we can do an exact value. They're done exactly the same. So for instance, here's another example where we're asked to evaluate, in this case, let's write this way, cosine of theta minus phi. So this is, again, just an application. Again, when you do the inverse trig, you'll do it like I've taught you before, but I want to give you more practice with these new functions here, these new identities. Now, what do we have? We have cosine theta is 5/13, and theta terminates in the 4th quadrant. So that's going to tell us in this case that X is positive, Y is negative. So the sine is negative, the cosine is positive, obviously. And then we're given tangent phi is negative square root 15. And of course, phi, well, here's one possibility. Phi terminates in the 2nd quadrant. Again, where X is negative and Y is positive. Okay, so when you think about doing this, you get the sines and the cosines with the theta and the phi. So what you can do, since now we have the right triangle approach, is just draw a reference triangle. So here the cosine is adjacent over hypotenuse. So we have 5 and 13. And now, of course, we can think of the square of 13, which is 169. And the square of 5, which is 25. And that'll give us a 4, and a 1. Well, that's just 12 squared. So we've got nice numbers. So we get a 12 here by the Pythagorean theorem. So now here, adjacent over hypotenuse, that requires that our theta be placed here. And so now we can define any trig function using this sign convention here. Now for this, remember, we can think of this as our reference triangle as the square root of 15 over 1 where everything's positive. So this is, let me just say this. I won't say equals, I'll just say reference triangle here. So this would be opposite over adjacent. So we have in this case phi opposite over adjacent. So we have square root 15. And here we have a 1. So now we're good to go. So if we square this out, we get 15 plus 1, which is 16, which is 4 squared. So this is a 4. So now we have the reference triangle with this sign convention. Okay, so that's important. That attaches the negative to the x. This attaches the negative to the y. So now let's write what this is. Cosine of theta minus phi by our new formula identity is cosine theta cosine phi. Now with the minus, remember we get the plus sine theta sine phi. So now just go ahead and fill it in. Cosine theta is 5 over 13. And now over here we need cosine of phi, but remember the cosine's negative because x is negative, and this would be negative 1 over 4, or just negative 1/4. Do your reference triangle and then write your arithmetic here. This is how I've taught you. Again, this is better mathematics. Everybody gets so sloppy when it comes to arithmetic of the unit circle, but I've taught you well, so please follow this convention. So now sine of theta, okay, let's go up here. Now notice the sine is negative because y is negative, so we have opposite over hypotenuse, so this will be negative 12 over 13. And now lastly, we have what? Sine of phi. Again, remember here the y is positive, so the sine is positive. So we have opposite over hypotenuse, square root 15 over 4. Okay, so that's it. That's it. The thing is that you're fine with working with the inverse trig functions, you know, where you define an angle and draw the triangles just like we did before. But now I want you to first get used to these new identities with the same type of setup here. So now we're good to go. So we've got the 13 times the 4, that's what our playing deck of cards, right? That's 52. And then we have the negative 5 minus 12 root 15, and we're done. So the idea here is nothing has changed. All the arithmetic is the same. We just have these newfangled identities, which we're finding to be very useful. Now what I want to do is just derive a bunch of new ones from the old ones. Now, you're going to think, I don't care about all these new ones, Professor Ron. They just seem to be, you know, thrown out there, and are we ever going to really use them? Well, here's the deal when it comes to these other identities. There will be times when you will have need of them. And I had a former colleague, she always said, make sure they know how to use these. And I said, well, you know, I agree. They should be familiar with them. But the thing is that as you need to use an identity, you get more familiar with it. Ones that are less used, not so much. So we'll just say 7.3, new identities from old. From old ones. And when I say old ones, they're the ones we just derived. So I have a list of all of these. We're going to start out with the double angle, and then we're going to do the half angle, and then the product of sum and sum to product. So first, notice our first theorem will be the half angle. Well, you know what? Let's not start with that. Let's start with the double angle. They're easier, and then we'll do half angle. It'll be a lot easier, and then the power reducing. So let's start with the double angle. So we're going to write down the theorems that we need from the sum formulas. So first, we recall that we have sine of A plus B. Now we want to replace the B with A. So instead of saying sine of A plus B, we're going to say sine of A plus A. So again, we're going to take A to be a real number. And then, of course, this is just sine of the double angle, sine of 2A, like sine of 2x. So what is that? Okay, well, let's just fill it in. This is going to be sine of A cosine A. And then we flip the arguments, but they're the same. Sine of A cosine A. Well, that we just get two of the same. So this is just 2 sine A cosine A. Wow, double angle. So what we see here, and I'll just kind of formalize it, sine of the double angle is just 2 sine A cosine A. You get a lot of use with this one. And students remember this because they remember the addition formula. So that's the double angle formula for sine. 2, this one turns out to be an extremely useful one because it gives us the power reducing, so to speak. Let's do cosine, but again, instead of doing A plus B, we're going to do A plus A. So this will be cosine of the double angle, hence double angle. So now when we do this, we say, okay, well, this is just cosine A because instead of having cosine A cosine B, we have the same argument. And then we have what? Minus sine A sine A. But that's just cosine squared minus sine squared. Oh, isn't that crazy? So cosine of the double angle is just the difference between cosine squared and sine squared. So it's not the Pythagorean. It looks Pythagorean, but a little kink right there with the minus. So there's one version. The other version would say, well, let's replace cosine squared with 1 minus sine squared. So this will equal 1 minus sine squared A minus sine squared. So that gives us 1 minus 2 sine squared A. So there's another version. And then, of course, we can replace the sine squared with 1 minus cosine squared. So you're thinking, why do we do this? Well, it's just whatever we need. These have become convention. So now you have minus minus, so you get 2 copies of cosine squared minus 1. So now we've got cosine of the double angle. We have one form, which looks Pythagorean, but not quite. And then we have the sine form, and we have the cosine form. So of course, if we're doing a quadratic equation and we need everything in terms of sine, we would use this. If we need everything in terms of cosine, we would use this. So both of these get plenty of use. You will use these all the time. Now the tangent one, not so much, but I'll write it down. Tangent of A plus A. We just say tan A plus tan A. Tan A plus tan A. And then we divide by 1 minus tan A times tan A. So that's tan A squared. So we get 2 tan A divided by 1 minus tangent squared. Now this doesn't get as much use. Again, not that it's, worthless, but we just don't use it as much. These get much more use in the calculus, but I want you to be aware of it. So these are called the double angle. So you're thinking, it's like, well, maybe not so good, because the unit circle, we think if we double angles, we already get an angle that's already on the circle, 60 plus 60, 120, 45 plus 45, 30 plus 30. So that's, maybe not as useful as the others, but algebraically, these are extremely important, especially 1 and 2. Now, the next thing we need is called the power reducing. Power, and all these, again, they can be hyphenated, the double angle, the power reducing. Now, the power reducing basically are drawn from this guy here. So we just look at these two forms. When we say power reducing, ladies and gentlemen, we take the squared term and write it in terms of first degree terms. So the first one is this, number one. What about sine squared of A? What does that equal? What about cosine squared of A? What does that equal? Well, what we can do is use the double angle for cosine. So for the first one, we're going to use this one. So we'll say cosine 2A equals 1 minus 2 sine squared A. And solve for sine squared. So we get 2 sine squared. Take this over and take that over. We get 1 minus cosine 2A. Now divide by 2. Sine squared A is now 1 minus cosine of the double angle divided by 2. This has extreme use with powers of cosine of sine with trigonometric intervals. So the square of the sine is 1 minus cosine of the double angle divided by 2. Now, how do we get this one? Well, we use that one right there. So we say cosine 2A equals 2 cosine squared A minus 1. Solve for cosine squared. So 2 cosine squared A equals now 1 plus cosine of the double angle. Divide by 2. Now, you need to practice doing these derivations. That way you will believe them. Because these have algebraic uses, extreme algebraic uses that we will use heavily in calculus. So these formulas don't get as much play arithmetically as the previous ones, but with the calculus, they are indispensable. So again, why this one comes up a lot, but this one now, the double angle gives us the power reducing. So now we write the square of sine as a first degree cosine, degree 1, power reduced. We write the cosine squared as a first degree cosine, power reduced, hence power reducing. Boring, but useful. And of course, don't go to sleep on me because when you get to Cal 1 and Cal 2 and you need these, you're going to think, well, why didn't I listen to Professor Ron?
Professor Ron, can you go back real quick? I need to finish the cosine.
Oh, I'm sorry, I'm going too fast. I'm sorry, I need to talk more. Good. That's the first time. Sorry about that, Jose. Is that good?
Yes, sir. Thank you.
Okay, everybody. Now, Jose makes a good point. All of these go on a note card. Commit to memory. Practice these derivations. Get up in the morning and start writing them down. Say to wake up, get your cup of coffee or your energy drink or your glass of orange juice or whatever it is that gets you moving. Write these down. Practice describing them to your friends. Teach these to people. Show them how you derive them, and then you will have them in your memory bank. Okay? All right, now, what do we want to do with this? Let's look at some other ideas. I'll hold this here and look at the half angle. You're thinking, well, we have double angle. Let's not discriminate with the half angle. So let's do half angle. There's one that's really, really nice, and the others are kind of rogue because we have plus or minus. So what we're going to do is we're going to replace, in this particular case, the A with A over 2. So now, look here. So we're going to do a replacement. So we'll say sine squared of A over 2. So replace A with A over 2 here. Now, of course, if we replace A with A over 2 here, the 2A becomes A. You're thinking, well, that's easy. So again, replace a with a over 2 here and here. And now use the square root principle. So sine of a over 2 of the half angle, you're thinking, well, this is no good. Plus or minus, I need to know where a terminates, right? Absolutely. Or actually, in this case, a over 2. So when you use these, you're like, well, here we are back to the arithmetic of the unit circle. So you would need to know where a over 2 terminates to use this. You'd have to choose either the positive or the negative. Of course, if a over 2 terminates in the third quadrant, you would choose the negative, right? Because the sign there is what? Less than 0. Now, same here. Replace a with a over 2. Cosine squared a over 2 equals 1 plus cosine a over 2. You know, folks, I derive all of these. I don't just say, well, here are the formulas, memorize them. That's not how I teach. I'm a mathematician, and I want you to become a better one. So you learn how to do this. Everything I'm doing, you need to repeat several times so you will know these identities. And the next time you see them, they won't be completely foreign. Now, square root property. Cosine a over 2 equals plus or minus the square root of 1 plus cosine a divided by 2. So there we go. You're thinking, not very glamorous, Professor Ron, and I agree with you, ladies and gentlemen. They must require a little more work because we have to know where the a over 2 terminates. So these are not as user-friendly, but that's what we call half angle. Now, the one that I want to do now is actually one more that's extremely elegant. And it's called the half identity or the half angle identity for the tangent function, which again is a remarkable result. So what about tangent? So here's what we're going to do. We're going to start backwards. So what about a over 2? What do we get for that? This is what Professor Ron calls a remarkable identity. It's not going to have a plus and minus in it. I don't care about the one that has plus and minus in it, and you shouldn't either. You get rid of my Norton virus protection. That's the best on the market, but it does tax your operating system. So now let's look at this and say, okay, how can we make this work in a way that uses what we already know? So here's what we're going to do. Observe. Here's a backwards approach. I'm going to use the half angle approach. So I'm going to say sine of a using the double angle, but I'm going to think of that as a double angle. So this is going to be 2 sine of a over 2 cosine a over 2. And now I'm going to use the cosine double angle form, but I'm going to use this one. I'm going to use this one right here. And let me focus this. I'm going to use this one. Oh, I lost it again. Every time I click over there, I lose my screen. Sorry. I can't, if I click outside my IPvo, it drops my screen. So I'll remember not to do that. So now let's use that. So cosine, in this case, of a will be 2 cosine squared a over 2 minus 1. Using this one right here, replacing a with a over 2. Equivalently, we have 2 cosine squared a over 2 equals 1, take the 1 over, 1 plus cosine a. I've worked on this for a while to try to take an idea that I learned the first semester that I taught when I graduated from A&M, and I thought this was fascinating to give you a formula that doesn't utilize the plus and minus. So now when we look at this and say, okay, well, how do we get something that's going to make any sense? So notice here, the 1 plus cosine A is this, and the sine A is this. But when we look at ratios of this, we get tangent of the half angle. So note, sine A divided by 1 plus cosine A will now be this, 2. I told you it was a little bit different. I had to work to get this. Sine A over 2, cosine A over 2. And now just go ahead and break this up into 2 copies of cosine A over 2. But now note, these absorb, the 2's absorb, and we're left with sine over cosine, which is tan A over 2. So there you have it. This is a remarkable formula, if and only if. And of course, you can conjugate this and rewrite it, but this is the most famous form. If you want to conjugate, multiply by 1 minus cosine A and divide by 1 minus cosine A, you can change up the form, but that's easy to do. But this formula is remarkable. And this is useful to find. Now the half angle are more useful, ladies and gentlemen. So you want to do the tangent of 15 degrees, you just take 30 over 2, and you know the tangent of 30 degrees. So this is going to give you some really nice exact values that the previous ones didn't. So we'll say half angle, useful for new exact values. So the beauty here is that we can get additional information in this particular case. So these formulas here kind of rogue, plus and minus, not the best. Got to work a little harder. But here, no work involved, no plus or minus, direct. That is truly remarkable. And this is the basis of the Weierstrass substitution in Calculus 2, which I will teach you if you take my class. If you make it to Cal 2, no, I'm just kidding. Of course you'll make it because you're going to work hard. This is the basis for the Weierstrass substitution. Weierstrass substitution. Guy was a genius that just thought math. Weierstrass and Bolzano are theorems are named for both of these mathematicians, and they came up with some beautiful results in real analysis. Okay, so another one for the record books right there, all of these, no cards. Now, the last set has to do with the, I want to say product to sum, and then I will finish up next class if I have time. I'll probably have time to go ahead and do the sum to product. But I want you to know these and then practice writing them and then practice doing some arithmetic with them. That is, I want you to know these because you can derive them from the simple formulas that we've worked on already. So the next one, here's my little technique. These are going to be called product to sum. And you're thinking, okay, Professor Ryan, where are these going to be useful? These are going to be useful in integral calculus. So what we want to do, and I'm going to show you the technique, we're going to pair these things up. So first we're going to start with sine of A plus B equals sine A cosine B. So back to the beginning, plus sine B cosine A. And below it, I'm going to write sine of A minus B equals sine A cosine B minus sine B cosine A. These are actually easy to derive, but I'm going to pair up the addition and subtraction formulas for sine and cosine to derive all four of them. And then cosine A plus B equals cosine A cosine B minus sine A sine B. Now, did you all, everybody get the last formulas? Did I go too fast? Did everybody get these? Jose, did you all get these? Okay, I just, if I go too fast, let me know. Cosine A minus B. Yeah, the end of the class, it gets a little bit more demanding, but it's only because we just, just putting a lot of ideas together. So we have cosine A cosine B plus sine A sine B. Okay, so what do we want to do with these? We want to add and subtract them. Okay, so our first one right up here, I want to add these two equations. So I want you to add. Let me do this. Let me use Roman numerals here. And I'll call this 1, 2, 3, 4. Now some of this will seem redundant, but I want to give you all the formulas. So add 1 and 2. Add 1 and 2. When you add 1 and 2, these absorb, okay? So this is going to give us 2 copies of this. So we get 2 copies of sine A cosine B. And that equals sine of A plus B plus sine of A minus B. Now divide by 2. So sine A cosine B equals 1/2 times sine A plus B plus sine A minus B. Now, how simple is that? That's basic arithmetic right there. Now you're thinking, I'm not going to remember these, Professor Ron. No, you remember these. You remember these 4 because you write them down every day. And if you need this in calculus, you just write these down, add them up, boom, there you go. So it's a lot easier, ladies and gentlemen, to integrate this than the product. This requires integration by parts. These are simple integrals. So this will be very useful to you in Cal 2. So how do you remember this? You remember 1 and 2, and you're done. Okay, well, you're thinking, now do I have to, can I just mix and match here, just like flip the A and the B around? Yeah, we're gonna be lazy. So for the second one, I'm not gonna add, I'm just gonna flip them around. So in this case, what about if we wanted cosine, let me write it this way, and then I'll turn it around. Say we want sine B cosine A. You want to flip the A and the B. So this will be 1/2, just be lazy. We get sine of B plus A plus sine of, now we flip them around, we get, in this case, B minus A. Well, this equals 1/2 sine A plus B. And now flip this around to A minus B and factor the negative because sine is odd. So now I'll just write it and do it in alphabetical order. Cosine A sine B is now 1/2 sine A plus B minus sine A minus B. So that's easy enough. That's the second one. Now you're thinking, do I memorize this? No. You either load this one and flip this around, or you just subtract them. Doesn't matter. If you subtract in this particular case, then you get 2 copies of this, and you get the same thing. But I just went ahead and flipped these 2 to get this for free, just like we did before at the beginning of class. So the product you're thinking, these are the same. Why do I need them? Well, they're always listed. And you're thinking, well, if I need this, I'll just call the A, B, and the B, A, which I did here. So you're thinking these are really redundant. I agree with you. But they end up in your list. So I want you to know it, or at least know how to derive it if you were asked to derive it. Now, for the next ones, for 3, I want you to add, let's see, in this case, I want you to add 3 and 4. Now you're thinking, why are these so important? Well, ladies and gentlemen, they come up in our calculus and mathematics. And so they are more fundamental identities than other identities. There are many, many identities, but these are so ubiquitous in calculus and in engineering math and physics that we learn them. Again, as an engineer or computer scientist, whatever you become in STEM, you will see these all the time. So now let's add, notice here, ladies and gentlemen, these will absorb. So let's add. So this is going to give us 2 copies here, 2 copies of cosine A, cosine B, equals cosine A plus B plus cosine A minus B. Now divide by 2. Cosine A cosine B equals 1/2 cosine A plus B plus cosine A minus B. And that's in the list here, that's the third one. Again, product to sum, product to sum, thinking the difference is a sum, product to sum. Now, of course, here, should we just be lazy again and just flip the A and the B? Well, we don't want to do that because these are going to be different. Notice these are parallel. The sine A, cosine B, they're parallel. They're just flipping the arguments. But here, this is not the same. When we subtract, we don't get cosines, we get sines. So now we've got to work harder for number 4. So I wanted to point out the difference there. So now what I'm going to say is subtract 3 from 4. So subtract, make it easy, subtract 3 from 4. Let's see here. Let me see. Yeah. So that means these are going to absorb. 3 from 4. Make sure my logic was correct. So that means the cosine terms will absorb. So now we get 2. So we'll do this minus a negative. So that'll be plus. So that gives us 2 sine A. You see why you have to have these equations to do this proof. Otherwise, it'd be a nightmare. And I'm telling you exactly what I'm doing. So I'm giving you a better proof than you get in the book. So we do sine A plus B minus a negative. So we get 2 copies. And here we're subtracting, these go away. So I get cosine A minus B minus cosine A plus B. And this is easy to remember. I tell the students that you get minus, minus, plus. So a bunch of minus signs. So we get divide by 2, sine A, sine B equals 1/2 cosine A minus B minus cosine A plus B. That's the last one for this set. So you're thinking, wow. So if I'm in calculus 2 and I need to integrate this, I'm going to use this identity because this will be easy integral. That would require integration by parts. All of these get used in calculus 2. They get used in physics. They're very, very important. Again, these get more use than the sum to product. Now, for the next case, the very last bit, I just want to flip these around very simply. So everybody got these? All these boxes filled in? Am I good to go on? I'm going to come back to this. Now, notice if we wanted to flip these around, we'd want to make these arguments here. Say if we wanted to write this as the sum to the product, we want the arguments to be nice and simple. So we're going to do a change of variable. So I'm going to keep this right here, okay? So here's what we're going to do. Now we want sum to product. You're thinking, when does it end? Well, this is the last one. Sum to product. So here's how we're going to do it. We let, I use alpha and beta. Let alpha equal A plus B. And beta equal A minus B. This is standard, but I want to use letters that you can remember. If I use letters that are easy to confuse, then that's not good. So now when I'm thinking, okay, well, how do I get these? Let's just see here. So now look, if I want to solve for all of these, and for instance, say, I've got this as alpha and beta, what's A? How do I do this now? So solve these. If we think about this, note, observe. This is the beauty of this. A equals alpha plus beta over 2. Why is that? Well, if you add alpha and beta, the B's absorb, and you have 2A, divide by 2, absorb the 2. And B, now absorb the A's, do alpha minus beta. Okay, well, if you subtract these, the A's absorb, and you have 2 copies of B, divide by 2. So now, here's your change of variable, right here. Change of variable. So now we just go for each of these and flip it around. So number 1, we have sine alpha plus sine beta multiplied by 2. So we have sine alpha plus sine beta multiplied by 2 is 2 sine alpha plus beta over 2 cosine alpha minus beta over 2. Right there, and I'm putting the parentheses just to make it clear, okay? So now, go to the next one. Do the same thing. 2, we'll do the same thing. We have sine alpha minus sine beta. Sine, now these only have sines or cosines, not mix and match. Sine alpha minus sine beta. This is what you can use to prove differentiability theorems and continuity theorems in Cal 1. Okay, so we have sine alpha minus sine beta multiplied by 2 and get cosine alpha plus beta over 2 sine alpha minus beta over 2. Okay, so again, we're just making the reverse process more user-friendly. So now you have a simple argument over here, and then you can build the arguments here by knowing alpha and beta. Now let's move to the next one. So now we have number 3. So we're gonna do the same thing. We have, in this case, cosine of alpha plus cosine of beta, cosine alpha plus cosine beta. So again, multiply by 2, cosine alpha plus beta over 2, cosine alpha minus beta over 2. All right, and then for the very last one, right here, we'll do the same thing for this one. Again, we have cosine alpha, and we have, oh, sorry, just did that one. Go up just a little bit more. So now 4, we have cosine beta minus cosine alpha. Notice they're switched around. So we have cosine beta minus cosine alpha equals, now multiply by 2 sine alpha plus beta over 2 times sine of B alpha minus beta over 2. Now you're thinking, Professor Ron, don't they want the alpha first? And they do. They usually like that cosine alpha to be written first. So you take the negative, hit both sides with the negative. Now, I'm sorry about that, but you know, if you wrote it this way, it's equivalent. But in the literature, they will hit this with the negative and hit this with the negative. So the cosine alpha term is first. So I'm going to write equivalently. So you'll notice this will be cosine alpha minus cosine beta equals the negative of 2 sine alpha plus beta over 2, and then sine alpha minus beta over 2. So when you look at these, for the general formula is usually here. This is the one that you see in the literature with the negative. There we go. And this one is the standard one you see. And this one. Now you're thinking, do we use these much? And the answer is no, not often. Now in Calculus 1, like I'm saying, when you're trying to work with difference quotients with cosine and sine, these are extremely powerful. These help you to produce the formulas for the derivative of sine and cosine using a more elegant approach, which I often do in my class. And also this helps you to work with continuity constructs. So the idea here is that these formulas do not get as much attention, but they are extremely important. The ones, like I say, that get most of the attention or more attention are these when it comes to integration. So when you do trig integrals, ladies and gentlemen, these will be important to rewrite the product as a simpler sum because this is an easier antiderivative. So these you will see more. You will see these in physics. You open any physics book, you'll see these, you'll see these. Now they're not abstract, but just remember, you derive these first. So I tell my students, what do you need to know all of these identities? You need to know 1 through 4. If you know 1 through 4, which was where we began the class, these give rise to everything in these two sections. This gives you this. Once you have this, you have a simple change of variable to these. So I do not recommend that you try to memorize these. I want you to know these and have your note cards ready. So again, the thing is, I could give you a test if we were face to face, and I'd say derive all of these formulas, and that would be kind of miserable if you didn't know them. But what I want you to be able to do is to take the addition and sum formulas, derive the double angle, derive the power reducing, derive the half angle, derive the formula for the a sine x plus b cosine x equals what? The square root of a squared plus b squared times sine of x plus phi, where tangent of phi is b over a. And then derive these and derive the half angle. So the way you get used to these new identities is you practice writing them like I have. Now, these again are more used in calculus, less arithmetic, but in order to be able to navigate my test, you need to know them. You need to know how to use them. And so first, it requires that you can derive them and understand them. As far as substituting values, that's simple if you have the identity. So today, what we're going to do, again, what we've done today is we've introduced some new identities. And then on Thursday, when we solve equations, we will use some of these new identities to reconstruct the equation, to make it quadratic, to get all of the trig functions to be the same so we can solve them using the techniques from college algebra. So the identities not only help us with calculus, but they help us to solve trigonometric equations, which come up in mathematics, which come up in physics, computer science, engineering. If you are a fan of any of the DC comics, again, that's just science fiction. But what is so neat is that the utilization of the Fourier analysis and trigonometric analysis, you'll see the characters writing on the dry erase boards. And you'll be like, oh man, look at all those trig functions. Ladies and gentlemen, that's real stuff. That's real mathematics. So even though they make it look glamorous, it's not glamorous, it's difficult. So make sure you can derive all of these formulas. And then on Thursday, we'll use some of them to actually solve equations. So I appreciate your attendance today. I know we had a lot of identities and things, but get all of these on a note card, practice deriving them, practice the examples I've done, and get busy on your WebAssign. And now, just like I said before, what was that example? Now you can do your law of cosines problem because you know what cosine of 75 degrees is. Again, the problem did not ask you to approximate, so that a lot of you have come to office hours and figured that out. So just remember that when you work problems, these identities help you to get exact values. So excellent, everybody. I hope you enjoyed today as much as I enjoyed talking about these topics. It's a personal favorite of mine. I love real analysis and topology, and you use these all the time. So you all have a great day. Enjoy the springtime weather. And if I don't see you at office hours, I'll see you on Thursday. Bye, everyone.
Have a good day, sir.
Bye.
Thank you.
Thank you.
Could you go back to the sum to product formulas, please, real quick?
Oh, sure. Sum to product right here.
Yeah, I just missed number 4.
Okay, right here. Good.
Yeah. Thank you.
Oh, you're welcome. Now you all, I know you're breathing. That's good. I thought you all had gone to sleep on me. But I don't know, I think that would be hard to do with me rattling on all the time. Yeah, these might look a little bit awkward, but as you start working with them, they'll make more sense.
All right. Thank you. Have a good day.
You too. Thank you so much.